Hello everyone. In this video, we're going to take a look at functional programming. So we've already seen procedural programming, which is a programming paradigm or a programming style in which we simply have one command executed after the other. We could have things like while loops and for loops that execute a set of commands over and over again, but otherwise we're just executing one command after another until the algorithm is complete. We looked later on in the semester at object-oriented programming, and this was a different way of thinking about programming. So you notice that within the methods of the object, we still have procedural programming, but now we're thinking about things differently. We're thinking about these objects as containing methods that can perform tasks and holding variables that are the state of the object, what it knows about the task it has to perform. And so we changed a little bit how we thought about the code, and it enabled us to encapsulate some of the behaviors. So remember, encapsulation means to hide the details and take a more abstract view of the program so that we won't get lost in the details. Functional programming is a little bit like object-oriented programming in that the point of it is to hide a lot of the details, is to give us a more abstract, in some ways simpler way of looking at programming. And that helps us organize our thoughts, keeps us from getting confused and overwhelmed by the details of the program. So functional programming uses functions to encapsulate solutions to problems. And each function takes arguments and returns a solution as the return value. We've already been using functions throughout the semester, but this time we're going to think about how to compose functions together, so put functions together to solve some problem. So each of these functions will solve a smaller problem, we put them together, and we can solve larger problems of interest. So one thing we're going to do looking at functional programming is we're going to make a rule that we're going to forbid what's called side effects. So a side effect is when a function changes variables that are defined outside of that function. Remember that functions have a namespace, so variables defined inside the function are in the function's namespace. Functions defined outside of the function are outside the function's namespace. So here's an example. I've written a function here called side effect. It takes two arguments. It sets global x. It's going to access this x equals 2 that was defined outside of this function's namespace. Then all it does is set x to be the product of the first and second arguments. And then we print x. If we run the function side effect on, for example, 3 and 4, and then print x, we're going to get this output. So at first, here where we see print x, it's equal to 2. When we run side effect, it now sets x to be 12. So when we print it, it's 12. So we modified a variable that was not in the scope, not in the namespace of the side effect function. So in general, that's considered to be poor programming. It's done a lot, but it's sort of frowned on because if we're modifying global variables, it's really hard to track down bugs because we don't know what function later on in the code might have modified some variable that we defined up in the global space. That's why Python makes you use this global keyword to be sure that you really want to modify a variable that was outside of scope. So a lot of functional programming languages, that is, languages that are designed to support functional programming, forbid this kind of thing. They don't let you modify variables outside of the function. And we're going to forbid that here as well. It just follows the programming style a little closer, functional programming style. So in the past, we've used functions that call other functions before. So recall this earlier lecture where we defined the for multiplier, just a for loop that multiplies all the integers in some range, starting at the start argument and ending at the end argument, and returns the total of that multiplication. And then we defined factorial. We noticed that this for mult already solves the factorial problem. Factorial is just a special case where we start at 1 instead of some arbitrary start integer. So when we use factorial, we call the for-mult function. So you've seen us calling functions within functions before. That's pretty common. Recursion, which is a big part of functional programming, is just the idea that functions can call themselves to do work. And we'll look at a lot of examples in a minute here of what that looks like. Recursive programs tend to follow a consistent pattern. They're going to break a problem into smaller and smaller pieces, and they're going to solve those small subproblems and then put everything back together to solve the larger problem. So let's take a look at this pattern here. So a functional recursive program is going to have a base case, one or more base cases, that's very, very easy to solve, that's trivial to solve. In fact, it should be the easiest possible version of the problem so that we can solve it really easily. And then we're going to have a recursive step. The recursive step is where we take all the small subproblems that we've solved and put them together. And this recursive step just increases the size of the problem that we can solve by a small amount. But when we do it over and over and over again, we end up solving arbitrarily large problems, so problems as large as we want. If you happen to have had mathematical induction in a math course, it's exactly the same idea. So in mathematical induction, there's a base case and there's an inductive step. In programming, it's exactly the same thing. We have a recursive step instead of the inductive step, but it's the same idea. All right, so let's take a look at an example. As a procedural programmer, we would write a program to multiply a set of integers like this. We would start off with some total that we're going to add to, and we'd have a for loop perhaps that starts at the beginning integer, ends at the end integer, and just multiplies each of these x values as we iterate over this range and adds it to the total. But let's think about how to solve this problem not like a procedural programmer, but like a functional programmer. So we want a program that multiplies integers between a start and end value. So the first thing we have to do is think of the base case. What's the easiest version of this problem that we can solve? The easiest version, and I should say there's always, like the rest of programming, there's always multiple ways to solve this, and we'll see a different version of this at the end. But for now, I'm going to say the easiest version of this problem is when there are only two numbers. That is, when the end value is only one integer away from the start value. If that was the problem we were solving, it would be trivial. All we have to do is say end times start. Pretty easy. Now, the next step is to think of the recursive step. So we have a base case, a really trivial, small problem to solve. What's the next smallest problem? Well, the next smallest problem might be to multiply 3 integers together. So we've already solved the case with 2 integers, and 3 integers is just 1 integer more. So let's dig into this a little bit more. What we're going to do is break it down so that we have our base case where let's give these names. So instead of start and end, we're just going to think about very small concrete problems. We're going to have 3 integers, integer a, b, and c. So the base case is where integer a times integer b is our whole solution. In our recursive step, we're going to go another step further and multiply that by integer c. Now we can do this repeatedly for any number of integers. We can apply this recursive step over and over again. So here's our base case, integer a times integer b times integer c, that's a recursive step. But we could apply that recursive step again and multiply by integer d. So the recursive step is going to reduce the size of the problem. What I mean by that is that at every step, as we apply this multiplication of the next integer, we're returning a single integer. Let me go over that again. So integer a times integer b takes two integers and turns them into one. It turns them into an integer that's just the product of these two. Integer a times b times integer c takes the product integer of a and b times the integer c, and again returns a single integer. So we've taken now three integers and turned them into one. Every time we do this, we reduce the number of integers we have to deal with. We reduce the difficulty of the problem because we're always only multiplying two integers together at every step. All right, so let's take a look at the code that actually does this. So the first thing is, of course, we have our familiar function definition. I'm going to call it recmult for recursive multiplication. It takes a start integer and an end integer. And here's our base case. So if end minus start is equal to 1, so there's only one integer between, there's only, the end and start are almost the same, right? There's only two integers to multiply here. And because we're doing consecutive integers, they're only one apart. All right, so if that's all we have, then we return end times start. Otherwise, if we're not in the base case, we're going to do the recursive step. So the recursive step here says return whatever the value of start is times the result of applying recmult. Now, even though I'm adding a 1 here to start, I'm actually reducing the size of the problem. Because every time we add 1 to start, we're actually multiplying by the next number up. So let's say start was 1, then start here would be 1, start plus 1 would be 2, and it would be 2 to end that's being multiplied by recmult. So it's actually a slightly smaller problem because there's one less integer to multiply. And I'll go through a detailed example here that shows you exactly how this works. I want to pause for a second and say that recursive programming, functional programming is beautiful and powerful, but most people when they first see it, it looks really confusing. What tends to happen is that after a few days or a week of practicing, it'll suddenly click. It's one of those things where if you do it enough, it'll suddenly become clear in a sort of flash of brilliance. But until that moment, it's going to look really confusing. So we're going to go through a lot of examples, and I'll describe a lot of different kinds of recursion examples. All right. All right, so let's go through a detailed example. And it always helps to have something really concrete. So let's start with 3 and 7 for our start and end values. And we're going to unroll the recursion. That means we're going to just trace through it like we have with previous algorithms. We're going to look at each step, what's going on. All right, so 3 and 7. We first ask the question, is end minus start equal to 1? Well, no, 7 minus 3 is not equal to 1. So we go to the recursive step. In the recursive step, start is equal to 3. We're going to multiply 3 by the result of calling recmult on this smaller problem. So in the smaller problem, start plus 1 is 4, and then we have our end value 7. Okay, so we're starting to build up our solution. If you look at the bottom, we have recmult 3,7 equals 3 times the result of recmult 4,7. So now we're going into the next recursive step. So here we're calling recmult, entering the function again. So this is the same function definition, but it's a different instance of the function because this function has 4 and 7 as its arguments, not 3 and 7. All right, so we ask the question again, is end minus start equal to 1? And it's not. So we ask the question again, is 7 minus 4 equal to 1? And it's not. So we don't execute the base case. We're going to execute the recursive case. So here start is 4. 4 times the result of solving the problem for a smaller problem. So here we have 4 is equal to start times the result of solving the problem for a smaller set of integers. So now we have only the integers 5 through 7 to solve. And so on. So now we increment 6 and 7. And now when we enter the function, this is true. If n minus start is equal to 1, so 7 minus 6 is equal to 1. So we're going to execute our base case. Remember, the base case is our smallest possible problem where we just have 2 numbers to multiply. So we're going to multiply 6 times 7 here and return that value. All right, so 6 times 7 is 42. We're going to return this value back to where it was called. So remember, whenever we return a value, it basically replaces the function, where we call the function, with that value. So here we have our call to recursive multiplication. It returned 42 here. So now we have 5 times 42, which is 840. Sorry, we have 5 times 42, which is 210. So now we're returning 210 back to the previous place where recmult was called. So now we have 4 times 210, which is 840. And so 840 takes the place of this recmult call that we had earlier. And we have 3 times 840, which is 250. All right. So if we look down at the bottom here, in our base case, we got 42, and we returned the value. We multiply that by the value of start here, which is 5, and do it again. Now we multiply by the value of start with, which was 4 in this previous call. In the previous call to recmult, the value of start was 3, so we multiply by that. And then we're done. So we've built up our final answer of 2520. It's always a really good idea whenever you're trying to understand a program to just put some print statements in so we can see what it's actually doing. It helps you spot any bugs, and it helps you build intuition about what the code is really doing. All right, and that's especially true with recursive programs because at first they are sort of hard to get your head around. All right, so I'm going to print the values. So print start, print end, and that'll give us an idea of what's actually happening at each step. I'll put a little divider here so I can tell when each function starts. All right. Okay, so let's go ahead and actually call the function with, let's say, like we used 3 and 7 in the example in the slides. Let's do that. All right. So the first time that recmult is called is right here. And then it just prints out the start and end values, 3 and 7. Then recmult gets called here. But this time it gets called with 4 and 7 because we're adding 1 to start. And again, 5 and 7, and again, 6 and 7. Let's actually print out the value being returned. can see what that looks like. So I can just say print and start. And print. Just going to put this whole thing into the print statement so I can see exactly what value is going to be printed here. Actually, a better way is probably just to have a temporary variable. So we'll say x, print x, return x, and then we'll have x just be this. And this is purely so that I can print out the values as they go. And let's do the same up here. So x is going to be and start. Let's try that. Okay, so we have the same values before. So on the as each recursive call happens, recmult gets a different set of arguments. First it gets 3.7, then 4.7, then 5.7, then 6.7. Then it starts returning values. So first it returns 42. Then 210, then 840, and finally 2520, which is our final result. So notice during this functional style program, there's no explicit assignment of values to variables. There can be, but you try and keep away from it. There's no x equals some value. So values are passed around purely through return statements in functions and by passing them into arguments to functions. So when I want to increment start on the next call, on the recursive call to recmult, I add one to it here in the argument. And when I want to get my values back, they're returned here by the return to the function that called recmult. All right. So I'm sure that was confusing. But just keep in mind, we're going to have a base case and a recursive step. The recursive step always calls the same function, but with a slightly smaller version of the problem. So in this case, every time we executed the recursive step, we called it with one less integer. So I'm adding one to the integer here. So we're increasing the size of the start value, which means we're decreasing the number of integers we have to multiply. All right. So as I said before, there's always another way of writing a program. We can also write our program with a different base case. In this case, we're going to have the base case just be a single value. So previously it was if we had two integers, we would multiply them together. In this base case, we have a single integer, just the end value. That's the easiest case. And all we do here is return that value. So we're saying that recmult, if we just had one integer, would just return the value of that integer. And our recursive step actually stays the same. We're still going to multiply by the start value whatever we get out of calling recmult where the start value is incremented by 1. The only difference really is that recmult will be called recursively one more time, because instead of stopping when there are two integers left, it'll stop when there's one integer left. So what you just saw was called linear recursion. And every problem that can be solved with iteration can be straightforwardly solved with recursion. But not every problem that can be solved with recursion can be solved with iteration. Recursion is a much more powerful concept. The kind of recursion you just saw is called tail recursion, And that's where you have the function, the recursive step, happening at the end of the function. So here you see that the return statement is at the end of the function that we're using. So this is tail recursive. Let's take a look at another example. So this is from the Exam 1 review. We wrote a palindrome checker. So a palindrome is a string that reads the same backwards and forwards. And our solution here was to first reverse the string and then just check to see whether the original string and the reversed string were the same. This is a procedural way of solving this problem. Let's take a look at a functional recursive way of solving the same problem. All right, so it's the same procedure. We're going to think of a base case, that is the simplest possible version of this problem. Then apply the recursive step to solve a slightly larger problem. And we're going to think about how do we reduce the size of the problem at each step. So the smallest subproblem would be a string of length 2. So we can check to see if the first character in our string is equal to the second character. That's the easiest palindrome to check, right? If we have the characters A, B, it's simple to check whether A is equal to B. The recursive step. If the characters at the end of the current string are equal, and all the subproblems are palindromes, then the whole string is a palindrome. So if we start off with a simple base case of 2 characters, the next smallest size problem would be to add one more character onto each end of the string. So instead of having a string of 2 characters, we'll have a string of 4 characters. And we can just check to see whether those new characters are also equal. And if they're equal, and the base case is true, so the innermost characters were also equal, then the whole thing is a palindrome. So the way this is going to shrink the problem at each step is we're actually going to start off with some string as long as we like, and then every recursive step we're going to check those end characters, the first character and the last character, to see if they're the same, and then remove them, and then solve the smaller problem of palindrome on a string with the first and last characters removed. So every time we go through the recursive step, it shrinks the string by 2 because it's removing the first and last character. And then we can solve the problem of, is this smaller string also a palindrome? And here's a program to do that. It's called palindrome. The first thing we do is we check to see whether the text we're dealing with has more than 2 characters. If it does have more than 2 characters, then we're going to check the 0th and the -1th character. So this 0th character is the character at the beginning of the string, and this -1 character is the character at the end of the string. If they're equal, then we know for these 2 characters that it supports the idea that this string is a palindrome, and we can call palindrome recursively on a string with the first and last characters removed. So now we're calling palindrome on a string that's slightly smaller. We're solving a problem that's slightly smaller than we started with. And we keep on recursively solving a smaller and smaller problem until we only have 1 character left. And if we have 1 character left, we're going to say a string of 1 character or a string of no characters is a palindrome. So if I just have the letter A, we're going to say that's a palindrome. All right, so here's an example. Or at least if I run the program on, was it a car or a cat I saw? Sure enough, it tells me true, that is a palindrome. Let's trace through an example, a smaller example a little bit. So if we unpack this, what we're saying is does R equal R? So do the outermost characters equal each other? And does A equal A? So we take off the R's, and now we're left with solving the problem of whether ACECA is a palindrome. We're going to check to see whether the end characters are the same. And does C equal C? And then we hit the base case, because we only have the E left, and we're going to say that if it's one character, it's true. So now we're going to say, does R equal R, and recursively, does A equal A, and does C equal C, and base case, which is always true. All right, so to get a better understanding of palindrome, let's do what we did with the integer multiplier and just add some print statements here so we can see what's happening. So I'm just going to print the current value of text to start with, and let's see what that looks like. And of course, we'll call palindrome on something. Let's just do race car for now. All right, so at each step here, so first palindrome gets called with race car, of course, because that's this call right here. Then it strips off the first and last characters. So we're left with ACECA. It loops, it recurs again, calls palindrome on CEC, and then finally hits the base case where it just has E, and it finishes. All right, so let's actually try and return or print out the return values here. So probably the easiest way to do that is just to print out this comparison. And this one here. I'll go ahead and add a little bit of text here just to show this is the base case. This is the recursive case. All right, so recursive step gives us ACECA. Recursive step, base case is true. So you can see in the base case, we get true, of course. The recursive step says true because it compared these outer characters. It compared C and C. This recursive step compared A and A, and it's true. And this one compared R and R. All right, so let's try this for something that's not a palindrome and see how it fails, or how it figures out there's not a palindrome. All right, so immediately in this step, it checked whether R is equal to 1, and immediately it realized that was false. Now this brings up something that's a little bit of a subtlety. In many programming languages, when you have a Boolean operation like AND or short circuit is called short circuiting. What it means is because AND is only true if both its arguments are true, as soon as it sees that one of the arguments is false, it doesn't even bother to evaluate the rest of it. It doesn't even bother to check whether this is false or true. It doesn't matter. This was already false, and so it just stops. it short circuits. That saves a lot of time if you can avoid checking things that you know don't matter because it was already false over here. But sometimes it can be a problem if you really wanted to evaluate palindrome anyway, whether or not this ended up being true or false. So let's try having the asymmetry be deeper into the string and see what that looks like. All right, so now it went further until it finally hit this comparison of E and 1, realized those are not the same, and returned false and stopped. All right. All right, so that was linear recursion, where we had a single functional recursive call at the end of the function. There's also tree recursion. So let's take a look at tree recursion. In tree recursion, we can have multiple calls to functions within a function. That is, multiple functions to the same function within a function. Remember the Fibonacci sequence from lecture 8, slides 1 through 17. Just to remind you, this is where we had a mathematical representation of how many pairs of rabbits we would have after some number of generations. Notice that mathematically this Fibonacci sequence was defined recursively. So we said that the number of pairs after the nth generation was equal to the number of pairs after the n-1th generation plus the number of pairs after the n-2 generation. Okay? So the sequence we ended up with was 1, 2, 3, 5. So we add up the previous two terms to get the next term. And here's the function we wrote at that time. It's a procedural function that has a for loop that just adds up the previous two terms. And notice this is called tree recursion because when we call the same function multiple times within itself, we tend to get these splits. You can already see it looks like a tree turned upside down. So the first recursive call would be here after the second generation. Then we have another recursive call and the third, and so on. All right, so let's take a look at our solution, our functional programming recursive solution to this problem. Let's just go over in detail the generations and the values of the sequence. So we're going to add here a 0th generation, so index 0, where there are 0 pairs of rabbits. It's a little bit different than this diagram where they start at the first generation. This is going to help us define our base cases. So for the first generation, we have 1 pair of rabbits. For the second generation, we have still 1 pair of rabbits. So in generation 2, this is the sum of the 0 and the first generations. Generation 3, we're going to have 2 pairs of rabbits. In the fourth generation, 3 pairs of rabbits. And the fifth, we're going to have 5 pairs of rabbits. So in each case, we get the next value by summing up the previous 2. So our base cases are that in the 0th generation, we'll have 0 rabbits. And in the first generation, 1 rabbit. So we have 2 base cases here to get ourselves started. In the recursive step, once we have 2 values, 2 base cases to work with, we can start saying the next Fibonacci number is going to be the sum of the previous 2. And here's our definition in Python code, and it looks almost identical to our base cases and recursive step. So it says if n, that's the generation, if generation is equal to 0, we just return 0. Else if n equals 1, return 1. And now the recursive step, we finished our base cases. Now the recursive step, we're going to return Fibonacci called on itself with n-2 plus Fibonacci called on itself with n-1 and then n-2. We sum those up, return those values, and that's our recursive step. Let's talk about binary search. So if you were looking for a particular page in a book, and I told you to look up page 400 in a very long book, you probably wouldn't do it by starting at page 1 and looking at page 2 and 3 and 4 and so on. You'd probably open the book in the middle, see what number you had there, what page number, and then based on whether that page number was larger or smaller than 400, you decide whether to look in the first half of the book or the second half of the book for the number. And in fact, you might repeat that process. So you might then search for the middle page in the first half of the book, if you thought it was in that half, and then continue the process. Each time you'd be narrowing down by half how many pages you had to search. So you're dividing the problem into smaller and smaller pieces, just like we've been doing with our previous functional programming examples. In fact, you're using a divide and conquer algorithm. What you're doing, in fact, is binary search. It's called binary search not because it has anything to do with binary numbers, but because you're dividing the problem into two every time you take a step. In the previous examples we had, the palindrome and the integer multiplier, we only reduced the problem by a small amount at each step. So with the integer multiplier, we reduced it by a single integer. We chopped off an integer at the front, and then solved the problem of multiplying the rest of the integers in the sequence. In the palindrome, we chopped off the end characters and then solved the smaller problem of palindrome on the smaller string, on the shorter string. With binary search, we're actually going to divide the problem in half every time. And that means we can solve the problem, because we're dividing the problem in half each time, very, very fast. And the reason that's important, and it's really what computer science, a lot of computer science is about, is not only how do we write programs to solve problems, but how fast do they solve those problems. So let me give you an example of why that might matter. There's a very famous problem called the traveling salesperson problem, but turns out that there's lots and lots of problems like the traveling salesperson problem where it's seemingly quite simple. You want to find the shortest path through a number of cities. So you want to visit some number of cities without visiting any one of them twice. What's the shortest way to do that? Sounds like a really straightforward, easy problem, but it turns out to be incredibly hard to solve quickly. So this table helps illustrate that. This is with the fastest known algorithm. If there are 5 cities, there are 12 possible paths that you have to search to see which combination of those paths are shortest. And let's just assume it takes 12 microseconds to investigate those paths. Now if we have 10 cities, there are 181,000 possible paths that we have to search through to find the shortest one. Well, it's not too bad. It takes less than a second to do that on a fast computer. If we have 15, now numbers are getting really big. We've got 4 times 10 to the 10 possible paths to search. That's going to take 12 hours, even on the fastest computers. And as we increase the number of cities, and these are still really small. If you've used Google Maps to find your way somewhere, it's looking at thousands of paths. In this case, with 20 cities, it's 10 to the 16. It's going to take almost 2,000 years for a fast computer to solve this problem. And then with 61 cities, still not a very big problem. It's going to take longer, far, far longer than the age of the universe to solve this problem. So the reason that Google Maps and Apple Maps can solve these kind of problems is they use heuristics. They use estimates. They cannot guarantee to find the shortest path because it's been proved this is how long it would take to guarantee finding the shortest path. So one of the reasons why this kind of problem takes so long to solve is there isn't an effective divide and conquer strategy. And that's really what computer science is about, is finding ways of solving problems quickly, or in some cases showing that a problem can't be solved quickly. All right, so let's look at binary search again, because binary search is a great example of a problem that can be solved very, very quickly. Because we were able to use recursion and divide and conquer to have the problem size every step. And for the rest of the semester, we're going to not only think about how to write a program to solve a problem, we're going to think about how quickly that program solves the problem. All right, so let's take a look at binary search. We're going to follow the same procedure that we did with palindrome and with integer multiply. So let's set up the problem first of all. We want to find the position of an item in a list when the list is sorted from smallest to largest, or return false if the item is not in the list. So this is like searching for a page number in a book where maybe some of the pages have been torn out. And I'm asking you either to tell me that the page is missing or where in the book the page is. All right, so here's a couple of examples. We could search for 3 in the following list, for example, and it should return 4 because 4 is, remember, 0, 1, 2, 3, 4 is the 4th position in the list, starting at 0. Search for 8 in the following list. 8 doesn't appear in this list, so we should return false. All right, so think about our base case first. The smallest problem size for this problem is a list with a single element. It's easy to tell whether that element is what we're looking for or isn't. If it's not, there are no other elements, so we must be done. We can return false. If it is, the only answer is that it's at the 0 position. All right, so the recursive step. Look at the item in the middle of the current list. If it's bigger than the item we are looking for, search the half of the list before that item, and the latter half of the list if it's smaller. Otherwise, check the single item list. All right, so there are 3 cases here for a recursive step. Either the item we're looking at that's in the middle is bigger than what we're looking for, it's smaller than what we're looking for. If it's neither of those, then either the element we're looking for is not in the list at all, or it is equal to the single item that's in this list. All right, how do we reduce the problem size at each step? Well, we're dividing the problem in half every step and applying our search algorithm to just that half. So at every step, we're doing half the work that we did at the previous step, or we would have had to do at the previous step. All right, so here's the code that I've written that implements binary search. This code actually just checks to see whether an item is in the list, returns true if it's in the list, false if it's not in the list. We'll add more code in a minute to actually return the position of the item if it was in the list. All right, so binary search takes an item that we're looking for and the list that we think it might be in. Just like our recursive algorithm that we developed here with its base case that looks at the smallest possible situation, and the recursive step that reduces the problem by half each time, we have our base case here and our recursive step down here. So the base case is very simple. It just says if the length of the list that binary search was given is equal to 1, then just check to see whether the item is what we're looking for. If not, so we have a larger list than 1 element, we're going to start chopping it down. So we're going to first of all select a midpoint. So the middle position in this list, notice we're doing integer division here. We don't want to get floating point numbers because we can't use floating point numbers as indexes into a list. So we're going to use integer division here. And the first check we have is the item that's in the list at the midpoint greater than the item we're looking for? Remember, this is just like if you're looking at a book and you opened it halfway and you check to see whether the page number where you opened it is bigger or smaller than the page number you're looking for. So we're just checking here to see whether the element that's at the midpoint is bigger or smaller than the item we're looking for. And because we're assuming the list is sorted, like the pages in the book, we can assume if the midpoint item is larger, then our item, if it exists at all in the list, must be in the first half of the list. If the midpoint item is smaller, then our item, if it's in the list, must be in the second half of the list. All right. And then the final case where the item we're looking for is not bigger or smaller than the item at the midpoint, then either we're done because it's not in the list at all, or that element is the item we're looking for. All right. So we accomplish solving the smaller problem here. So we're going to give binary search not the whole list that we were given. We're only going to give it half the list. All right, so let's look at how these recursive calls shrink the problem at each step. So if the item is less than, if the item we're looking for is less than the item that we found at the midpoint, then we're going to call binary search on a smaller version of this problem. And it's smaller because we're going to use list slicing to just give it the first half of the list. Remember list slicing from our lists and arrays lecture. We're going to use this to give up to the midpoint of the list to the next call. If the item was actually larger than the item we found at the midpoint, we're going to use list slicing and give the binary search just the second half of the list. So we're going to go from the midpoint and up. That's what this column means. Slice out that second half of the list and call binary search just on that second half. So each one of these calls is only having to search half the list each time. And then if there's only one item in the list, or if the item that we looked at the midpoint is not larger and not smaller, it's going to either be the item we're looking for or the item we're looking for is not in the list. But either way, we're going to return just the value that's at the midpoint. Now I have to put, it's a little bit strange here because I'm saying return the value at the midpoint, not a range. I'm not getting a sublist here. I'm just getting a single element. And I have to turn that back into a list because binary search expects to get an item, which is probably an integer, and then a list. So I'm making sure this is a list by putting square brackets around it again to make it a list. Okay, so we've added a little bit more code here to keep track of the position of the item once we find it. So you can see here that we return the midpoint where we found the item. So if L midpoint is equal to the item, then we return that midpoint. And then we have a check here to see whether the return value from the recursive call to binary search, which we're calling val just temporarily, whether that was false or whether it was a legitimate position. If it was false, then we return false again. But if it's a position, then we add it to the current midpoint in this recursive call and return that. And that will add up all the midpoints that we visited on the way to finding the correct entry and give us the position in the array. All right, so let's explore this binary search code a little bit, see if we can get some intuition about how it's really working. The first thing I'm going to do is just check to make sure that it actually gives the right result. So I'm just going to print binary search. And let's search for -5 here. We'll give it the list. it says it's in position 1. Remember, we have zero-based counting, so 0, 1. That looks correct. Let's make this a little bit more flexible. So let's have the item we're looking for be read from the keyboard. I want it to be an int, and we're going to use the input function as usual. Put search item, or prompt with search item. Okay. All right, let's run this again. Let's search for 1 this time. Yep, that's the right position. How about we search for something that's not in the list, like 10? False. Great. So it seems like it's working. Let's print out the value of the list that's being passed in at each point. And let's search for 3 this time. Okay, so on the first call to binary search, it gets the whole list here. On the second call, it's cut that list in half. Then on the third call, it's cut it in half again. And then finally it returns the value. So let's print the value of the midpoint as well. Let's put 99 this time. Oops. Do this after we actually create midpoint. Now we can see where it's cutting it off. So it's cutting off at 3, 0, 1, 2, 3. And it passes everything after 3 onto the next recursive call to binary search. And so on. So the midpoint here was 3, and then 1, and then 1. All right, so that was our first lecture on recursion. I'll go over plenty of examples to try and make it clear, and we'll spend at least the next week on recursion because it is very, very important. It's something that's used along with object-oriented programming to implement recursive data structures. And recursive data structures are how computers store most data. They don't normally do it in lists and arrays in real programming. They normally store it in things called trees of one sort or another. And those trees are accessed through recursive programming. So I look forward to talking about recursive programming with you in our interactive session on Wednesday and Friday. Bye-bye.